Okay, make page table smaller. So from previous chapter, we see that the page table take pretty decent amount of memory. I mean, if there is a large number of the processes, then the size of the page table itself is pretty big. So it's pretty hard, pretty large to afford in a computer architecture cache, of course. It's infeasible. So we should place the page table in a memory. But if we just make the page table as an array, then yeah, it'll take a pretty large amount of the memory space. So for example, for 32-bit address space with a 4 kilobyte page, then I told you that we together track that the page table for each process take up 4 megabytes. So if there are 200 or 300 processes running in your system, they take like a gigabytes of the memory in your system. This pretty incurs a lot of the overhead. 그러니까 보통 32비트 머신이면은 메모리가 얼마쯤 쓰겠어요? Usually, if it is for like a 32-bit machine, then usually the maximum main memory will be 4 gigabytes. But if you're running 100 process, which occasionally happen in your system, 여러분 뭐 돌리면은 100개는 돌리고 있거든요. 지금 my PC at this moment, I'm sure that they are running more than 100 processes. Then they take like a 400 megabytes. Then this is like a 20%. It's like a 10% of your main memory is used for maintaining the memory itself. So paging was introduced to moderate the internal fragmentation issue and external fragmentation issue, but it may it may bring more drawbacks than internal and external fragmentation. If we just use a page table in this nightmare, people have devised an idea for reducing the size of the page table. Here, the point is that a page table, most of the entries are actually not in use. They are just marked as an invalid one because system does not give large memory for each process, but give only fraction of the memory for the address space, for filling out the address space. 우리 이야기했지만 address space는 이만큼 크지만 실제로 memory allocation 훨씬 적게 들어가죠. 그러면 어떻게 돼요? 페이지 테이블 대부분 엔트리가 뭐냐면 빈꽝이란 말이에요. 빈꽝. 이거 못 쓴다라는 거 표시하려고만 있는 엔트리란 말이에요. So page table have a very contain information in a very sparse manner, but just take a lot of memory space. So people have devised to reduce this amount of the memory consumption. So in your textbook, it concerns about 4 different approach. The first approach is a pretty naive one. Just to use bigger pages to reduce the number of the page entries. This surely reduces the size of the page, isn't it? 이렇게 하면은 당연히 줄겠죠. But what will be the problem for this approach? That is what you can find in your answer of the midterm question number 3, I guess. Yeah. 그렇죠? Yeah. So I don't mention that. Okay. So this doesn't make a general solution. So let's look into the other 3 options, and especially the last 2 is actually what we use in our system. And the second idea also makes sense. The second idea is a hybrid of the paging and segments. By how? By providing per segment page table. Here, idea is that instead of having one big page table, why don't we have a page table for segments? So think of bringing the idea of dividing memory trace into 3 different regions. So maybe, so here in this, as shown in this example, here the white color one is what actually in use, and gray color one is something that is not in use. Okay, and here, although they are segregated into pages, you here see that some of the series of the page, consecutive page correspond to segments. So you here see that there is a code segment of these 3 or 4 pages, and then here we have a series of a bunch of the pages for heap segment, and then also we have a consecutive series of the pages for stack segments. Okay, so why it matter? I mean, if it is naively represented in a page table, it will be something like this one. And what you can see here is that most of the portion for the page table is just wasted for just marking that these pages are not in use. But what if we divide that into 3 pieces and give an independent page table for each one? Then what we can have is something like this one. So check this one. This is a page table for code segment. And this is a page table for heap segment. And this is a page table for stack segment. And what you note here is that within a segment, only first few pages are allocated. And the remaining is just, we can assume that they are, we just regard them as something that is not in use. So here, what we make is that if we divide the page table, we can represent page table as a variable length table. Variable length table. So if there are some pages that is totally not in use, we don't need to have their entries, but keep the size of the page table in some buffer. In where we already had 3 pairs of the base and bound register set there, instead of having actual base and bound registers, I mean address point, but instead we have a reference to the page table for each segment. Yeah, so here the idea is that we have, why don't we have a 3 page table for 3 segment and allocate a variable length memory region for holding each page table. And this can be possible by using existing base registers, which will point now the beginning of the page table, and bound register, which represent the number of the allocated page entries in the segment. Okay, so for example, this is a 32-bit machine. So for example, in here, maybe we use the earlier 2 bits as a segment number, as an identifier of the segment. So possibly we can map that 01 means code segment, 10 is heap, 11 for the stack. Okay. And then translation might be happening this way. First, what it does is extract the segment number, by this operation. And then what? Extract virtual address number. And then this is a lookup from the page table. First, what it first find is finding the starting point of the corresponding page table with the segment number as a kind of an index, because we have 3 pairs of the base registers. Yeah. So if it is a 01, then it points to this page table. If it is a 11, it points to this one. If it is a 10, it's this one, and 11, this one. So we have 3 different page table, and they can be selected by segment number. And then what? It'll retrieve it'll find the page table entry based on the VPN number as a kind of the index number within each page table. And page table here. So for example, if the process acquires another page for code region, then this entry will be increased. However, yeah, such thing does not frequently happen. And even if it happens, yeah, application acquires pages in a consecutive to the existing one. So these segmented page table will not be sparse as original single page table. That's the idea here, to reduce the amount of the memory given to a page table. Do you copy here, this one? 그러니까 어떻게 하는 거예요? The main idea here is pretty much the same as the original idea of the segmentation. By dividing the memory region, we can make the memory region more continuous within each piece, within each segment. 그러니까 세그멘트 아이디어라는 게 뭐예요? 프로그램이 메모리를 다른 종류로 쓰는데 다른 종류로 쓰려고 하다 보니까 넓은 영역에다가 나눠놓고 띄엄띄엄 쓰더라는 거예요. 그럼 영역별로 쪼개면 어떻게 되겠다는 거예요? 영역별로 쪼개면은 훨씬 더 연속적으로 쓰고 있거든요. 그러면 똑같은 거예요. 여기서도 영역별로 페이지 테이블을 나누면은 스파이스하게 페이지 테이블을 가지고 있을 필요가 없고 연속적으로 가지고 있기 때문에 불필요한 공간이 많이 줄어질 거다. 이게 이제 세그멘테이션 페이지 테이블 아이디어입니다. 네. You will understand. You will understand. Don't worry. Yeah. You will get to the understanding. Okay. Okay. So, but what will be the drawback here? What will be the drawback for the segmentation approach here? All the drawbacks of the original segmentation idea consistently happen in page table issue in this case. 예, 우리가 세그멘테이션 공부했을 때 세그멘테이션이 갖고 있던 여러 가지 그 한계점들이 있을 수 있죠. 그게 그대로 여기에 있을 수 있습니다. For example, okay, here once we use variable length memory region for maintaining page table, how can we manage those memory for the page tables? They will suffer from what? They will suffer definitely from external fragmentation issues since variable length memory regions are given. 그렇죠? And what else? There are many more, but I do not go into the detail. Just leave it to you to study by yourself. I just check them in final exam. 네. 수업을 좀 띄엄띄엄 할게요. 수업을 띄엄띄엄 해야지. 네. Okay. So that's kind of nice idea, but here we have more fancy idea. Multi-level page table. This is actually what we use. What we have. The same idea is actually what we have in x86 machine. 진짜 쓰이는 겁니다. By how? Yeah, if it is sparse, then what? Why don't we represent page table as a tree? So to shrink the unallocated memory region easily. Here the idea is that why don't we make a two-level page table in this way? So these are actual page table, but we can have a one index page table or directory table here. So make a two-level page table. What's the benefit? So what if these leaf nodes, these are just nothing more than page tables in itself, then what will be the benefit? What if one node is totally something that is not in use? Then we don't actually have this entry, but just mark that all of these belonging entries are unused. In this way, we can save amount of the memory for representing page table. So the idea here is that divide the page table into a same size of the page units. But here the size of the unit should be the same as the page size. 그러니까 예를 들어서, for example, if the system uses a 4 kilobyte page, then page tables are segregated into a series of the 4 pages, 4 kilobytes. Why? Page table should be containing page as well. Main memories are managed in a unit of the pages. So page table is also data that should be loaded on a memory. So it should be also placed in some pages. So it would be better to control them, manage them while considering the size of the pages. So just segregate it into a and allocate a page to each page table piece, each page table unit. Okay? But do not allocate a page, do not give an actual memory if the corresponding unit has no valid entry. Why? Because the whole continuous regions are not in use, which happen more commonly in page table. And now we have an organizer, which is a page directory, as an index of an allocated page for page table. So in this way, so this is the original page table. Suppose that they can be divided into, these 4 pieces, and each piece is exactly in the size of a one page. For representing this page table, we don't need to have an actual memory for this region and this region. But what we need to have is this one and this one. So we can turn this into a tree representation. So these are here. This one is represented in this page, and this one is represented in this page. However, no allocation for page 1 and page 2. And here we have an index system, directory system, where it says that, yeah, first unit of the page table can be found on frame 201, which is in here. And there's a piece of the page table. And the next one, yeah, we don't actually need no data for representing one. Why? Because whole page table entry corresponding to this piece is what? All invalid. All invalid. The same for the third one, all invalid. And what about the fourth one? Fourth one, you can find the contents at the frame number 2.4. And this is 2.4. And here we can find one piece of the page table. 그렇죠? So originally we had like 4 pages for containing whole page table, but as we turn in this way, we don't need to have these two. So within 3 pages, we can represent whole page table. 그렇죠. 네. So this example is so simple that the saving is just a 1 page. However, if we concern large page table, yeah, saving, the benefit of page saving will be much larger. Yeah. And so here's an example. So thinking about address space size. Sorry for the typo. Address space of the 16 kilobyte. 16 kilobyte is the 14, and here we have a 64 byte pages. 64 byte is what? 2 to the 6, I guess. 그렇죠? 2 to the 6, I guess. And how many page table entries should be there in page table? Which is, yeah, this number of the BPNs should be there in a page table. So if we assume that PTE takes 4 bytes, then what? Page table take 1 kilobytes. And 1 kilobytes of the array will be contained in 16 pages. And yeah, which will be like this one, which will be something like this one. And here, what we can assume is that among these 256 VPN, only 6 of them are in actual use, and the remaining 250s are not in use. This is a kind of a realistic situation, by the way. 실제로 이럴 수 있죠. Which means that like only 3% of the page tables are actually used, but remaining 97% are actually not in use at all. 그렇죠? So a lot of the memory will be wasted. So here, the first 2 is for code, used for code, and in the middle there are 2 for heap, and at the end, at the tail, the 2s are used for the stack. Yep, and there is a lot of 256 BPNs are there for representing this page table. So how can we resolve this situation? I mean, how can we reduce the amount of the memory for this page table by bringing the multi-level page table? 이거 어떻게 할 수 있을까 생각한 거예요. So here's one idea. Thinking in this way, so we here use the 5 bits, I mean the last 6 bit as a kind of an offset, because this is the size of the pages. 페이지가 2 to the 6니까 the last 6 bits should be used as an offset, right? And we have like 8 bit for representing BPN, and why don't we divide this 8 bit into a 4 and 4? 4 and 4. And considering 4 bit in a page directory, I mean, this should be an index for the first level. And then we should use the remaining 4 bit as an index for the second level in searching the page table. Okay, yeah, 이거 이해돼요? So first level is this one. 4 bit is used for indexing the first level, and then the remaining 4 bits are used for indexing the second level page table. Okay, 4-bit. So this should be coded as a page directory index. Page directory index. And since it have a 4-bit, how many entries should be there? 16, 2 to the 4, 16. 16. And if we give a 4 byte for each entry, 그러면 어떻게 돼요? Page directory should take 16 multiplied by 4 bytes. This is 64. So it's affordable within a single page. 페이지 하나에 다 넣을 수 있죠. Okay. And here we have a page table index. The same here. This is a partial page table index. How many entries should be there? 2 to the 4. So it have 16. And if we give a 4 by 4 representing each page table entry, then it's a 64. So it's also foldable within a single page. 그렇죠? So this is an example. So this is a page directory. Page directory is what? You can think of it as a kind of a parent node. This is a parent node. And how many children that it possibly has? Total 16. However, as you can find in here, yeah, most of the regions are not actually in use. So what you can see here is that these are the page table index bit, and among them, what you see is that only 000s are in use for these 4 pages, and 1111 is used for indicating these 2 pages, but the all others are actually not in use at all. 그렇겠죠? So for example, here we have a 0000s. We need to have a 1 piece of the page table, and for the 1111, we need to have another piece of the page table. But what about the others? The others are not in use. Okay, so this is what page table directory shows. So first entry is what representing the case for 0000. For this case, what you need to refer is a frame number 100. Make sense? And for the last one, 1111 case, what you need to refer is a frame number 101. So once we go to the frame number 100, this is that. This is that. And what you can find is a piece of the page table that corresponding to this case. And here what you can see is that 0000, 0000. So this was this one. So you can find it from the frame number 10 and 0011, 0001. This is for this case. And then here, this is a case for 0100, and this is a 0101. Yeah, these two corresponding to these two, and remaining are what? Just unused, just invalid. They are unused pages. And going to the frame 101 here. So all things are unused up to the point here. This is what? This one corresponding to this one. This one is 1110, and this is a 1111. Okay. So how many pages are now in use? Only within 3 pages, whole information for the page table is fully contained. But it will taking 16 pages if it's just naively represented in the form of the array. So this is how we can save a memory by using multi-level page table. 신묘하죠? 네, 신묘합니다. 네. Okay. This is pretty good, but here we have a kind of a, I mean, this benefit of saving memory space doesn't come freely, but what? It takes some cost in time performance. Why? Since we have a 2-level page table, when we refer page table, we need to have at least 2 memory accesses. One of the benefits of using array style page table is that we can directly find the page table entry. 그렇죠? However, since now page table is structured as a tree, we need to take down from the top to the leaf. So it involves more memory access for referring page table. So there's kind of a trade-off between memory efficiency and time efficiency. Here, memory efficiency is so low, so we here just sacrifice a little bit of the time efficiency to have a benefit in managing the memory space. So multi-level page table is based on that idea. And for like a 64-bit address, I mean, for today's 64-bit machine, I know that what I know is that architecture sometimes use a 3-level page table. Yeah, because address space is tremendously large, so it should have 3 different layers of the page table. Then the time for updating page table, accessing the page table will be much higher, much severe than the one for the naive approach. However, if we have plenty of the TLB entries, page table lookup does not frequently happen. So the cost for maintaining the page table will be moderated by that. Okay. Last idea is inverted page table. Inverted page table not having page table per process, it just to keep one big single page table for the system that have an entry for every frame to indicate to which process and to which VPN of the process the frame was given. So inverted page table is pretty memory efficient because we just keep one instance of the page table in a system. But drawback is what? Yeah, we need to do some linear search or hashing for finding a proper entry in a page table when we are looking up the frame number for a given VPN. So this is a more ultimate form of sacrificing the time efficiency for improving memory efficiency in this case. I think I already have introduced the concept for the inverted page table in earlier lectures, so I just quickly skip this up and finish